We're back with Chapter 5, Control Volume Approach and Continuity Equation. I'm going to remind you here that of what we're doing, our learning objectives. This is Section 5.2. So we will be talking about these sections here, these topics. We're going to describe first the types of systems that engineers use for analysis. Basically, we're going to have a discussion of closed and open systems, and we're going to list the differences between a control volume, or discuss the differences between a control volume approach and a closed system approach. The CV, or control volume approach, is an Eulerian approach, and the closed system approach is the Lagrangian approach. We're also going to describe the purpose, application, and derivation of the Reynolds transport theorem. And at first, this is going to seem quite abstract. So hang in there. I think it makes a lot more sense once we start using the Reynolds transport theorem. But in order to get to the point where we understand how to use it, we need to understand where it comes from. I would say that Section 5.3 is one of the most important sections of this semester. You must understand the control volume approach in order to understand how to solve problems using mass with the continuity equation, momentum with the momentum equation, and energy with the energy equation. So this is going to be extremely important for not only the rest of Chapter 5, but also Chapters 6 and 7 on momentum and energy. So let's skip forward. This is also going to be probably a fairly long lecture, but let's get at it. So the control volume approach. Engineers solve problems in fluid mechanics using this approach. The equations for this approach use what is called the Reynolds transport theorem. It's going to be a general theorem which is going to relate a Lagrangian point of view, a Lagrangian way of expressing the equations in terms of a total derivative with respect to time on the left-hand side of the equation with the Eulerian approach on the other. Remember that we can express a system in terms of either Lagrangian or Eulerian, and they're equivalent. It's just that in many cases in fluid mechanics, the Eulerian approach is going to be easier for solving the system, the problems. So think back to Chapter 2. What are some of the defining characteristics of a system? Systems are classified into two categories, closed and open. This is going to basically lead us to the Lagrangian closed systems, and where we just track an individual fluid parcel and don't allow things to cross the boundary of a fluid particle, and the Eulerian approach where we look at things basically as they're passing by us. When we look at closed systems and open systems, or the control volume way of looking at things, we also like to think of a control mass. And so in the Lagrangian point of view, this is going to be a fixed collection of matter. This is really what we call our fluid parcel, or our fluid particle. Something that never falls apart. We can just track it all the way through its journey in a fluid flow. And in this case, mass cannot cross the boundary, but the boundary can move and deform. So we can have stretching and warping and even kind of rotation of the boundary, but we cannot lose any of the fluid from within that particle. Here's an example of a closed system where we have a piston, and this is sealed off through this piston here, or through this enclosure, and then the piston pushes down on this, and we can change the properties of in this case, the air inside the cylinder. We can pressurize it or we can depressurize it by changing the piston, but we are not allowing this system any exchange of matter of this with the outside world, outside of our little system boundary, which is given by this little dashed box here, square. So now let's look at what we mean. So that would be a closed system. So now let's look at what we mean by a control volume. And in this case, remember that this is kind of synonymous with an open system. So in the control volume approach, we use this idea of a control volume. We call it a CV, and it is specified. It's a specified volumetric region in space that we have to select, and normally we will be selecting a control volume in such a way that it's advantageous for us to solve a particular fluid mechanical problem. So one of the things that we're going to have to be able to do as engineers is to choose a convenient control volume. And this isn't too bad. The matter inside a control volume is usually changing with time because mass is flowing across the boundaries, and that's again our Eulerian approach. We're allowing, it's like looking at a cross-sectional area of a river as it flows through that basin. Control volumes can be fixed, or they can actually be deforming in time. Most of what we'll do, we will actually have fixed control volumes, but not always. And here's an example of a control volume. This is a control volume, is the water inside this tank, but our control surface now is being drawn around that volume, and that our dashed line is the surface. So you can see in this case we have our CV. It's the volumetric region surrounding the tank. It includes the entire tank. It includes this inlet and the outlet. And our control surface is that surface that basically bounds the volume. Engineers use this approach, or these two different approaches, when choosing how to solve problems. And so this flow chart can be very useful for trying to identify which route you want to be, which route you want to take for the solution of a given problem. So a system. Whatever the engineer selects for study is the system, and it can be either a closed system or an open or a control volume. The closed system, let's take a look at this side. This is going to be the Lagrangian approach. We're going to take a Lagrangian view. The collection of the matter is going to remain fixed. It can be either a particle or a system of particles, and it can either be a rigid body or an isolated system where we allow no work or heat to transfer on the boundaries. It turns out this can either be like an isothermal or what's called sometimes an adiabatic system, where we're not allowing heat energy to be exchanged in the boundaries of the system. So we're allowing for a closed system. If we go down the other branch, we're choosing an Eulerian view. We're going to choose a region of space which we're going to bound by our control volume and our control surface. And as I just mentioned, these can either be fixed boundaries or they can be deforming boundaries where the volume is constant with time or changing with time. So we have a similar chart to what we had before, where we are looking basically at a Lagrangian approach versus an Eulerian approach. And the basic idea in the closed system is we're going to be analyzing a body, a fixed body or collection of matter. And in the Eulerian approach, we're going to analyze a spatial region, some sort of region that we're going to allow things to be transported across the boundaries of the control surface. This is Lagrangian versus Eulerian. Mass cannot cross the boundaries in a closed system, but it can in a control volume approach. The mass of the closed system must stay constant in time. Since we aren't allowing anything in or out, the mass has to remain constant in time. But in general, this isn't always the case. The mass inside the control volume can be constant, or it can change in time. We're not going to specify that ahead of time, and the Reynolds transport theorem will allow for either type of system in the control volume. The mass identity is always going to be the same matter in the Lagrangian approach, and in a control volume, the mass is going to be changing at all times. We're going to have matter coming in and out of our control volume and surface and through the surface. So the different applications are, really you've been doing a lot of Lagrangian closed system work when you've worked with solid mechanic problems. We sometimes use this for fluid mechanics, but it's also used for thermodynamics and other sciences. However, it's very useful for fluid mechanics to use the control volume approach as well. And it's sometimes used in thermodynamics and other things. So let's dive in a little bit more to what we mean by the control volume approach. Let's derive some equations that describe this. And what we're doing is we're leading up now to what we mean by the Reynolds transport theorem. So we need to have some definitions. First of all, let's look at what an intensive versus an extensive property is. So we're going to define a variable capital B. And capital B is going to be defined to be the mass times B. So whatever B is going to be some property that's going to be representing our fluid. It's going to be a fluid property. Maybe it's momentum or energy. Whatever that B is going to represent the amount of that parameter per unit mass, because this has got to be B over M times M gives us B. So basically, B has to equal capital B over M. It's the amount of that parameter B per unit mass. B is termed the extensive property, and little b, lowercase b, is termed the intensive property. And even though our book does not list some examples of that, I grabbed some stuff from Young's book to show what this would mean. So if we're interested, as we will be in continuity, if we're interested in mass, where our quantity of interest is mass, then capital B is mass, and that's the extensive property, and the intensive property is mass over mass, which is just unity, M over M. Now, if we're interested in an extensive property of momentum, we can see that if we divide the momentum by mass, the intensive property is velocity. And correspondingly, if we're interested in kinetic energy, the intensive property is going to be 1 over 2 v squared. Or 1/2 v squared is what I should say. Okay, so we have somewhat of an idea of what the extensive properties are and the intensive properties, capital B and little b. So we remember now that B equals, for any point in space, the capital B over mass. Now, the amount, we can now start to specify how much of a quantity of the extensive property, of the amount of an extensive property, might be contained in a certain volume. And of course, we're interested primarily in what our control volume, what is in our control volume. We're going to need to track that in order to, in the Reynolds transport theorem. So we can take B, and we can just, since little b is B over M, we can just integrate little b over M, and that will give us the amount of our quantity that's in our control volume. And we can break out dm into rho dv. Now this is starting to look a little bit like our flow rate, if you remember from section 5.1, and that's exactly why we talked about Q and also the mass flow rate. We'll see those things kind of come back into play here in a minute. So here is a look at a nozzle that's starting out with a larger diameter, kind of necking down to a smaller diameter here. And we've got the velocity of flow coming through here in one end, and we have velocity going out the other. We have chosen this dashed line to be our control surface, and inside that control surface is our control volume. We can begin to specify things about this control volume. We note that at either end we have a cross-sectional area whose normal is outward from the control surface. So in A1 is pointing, this control surface is basically pointing back directly into the flow, whereas A2 is pointing basically out the other end of the flow. Note that V1 and A1 are in opposite directions for this case, whereas A2 and V2 are in the same direction. So when we work out these dot products, the cosine basically, these are in the same direction, so the cosine becomes 180 degrees in this case. These are 180 degrees off, so that's a cosine of 180 gives you -1. And in this case, we have the cosine of 0 because they're in the same direction, and that gives 1. So you can see that naturally, once we have specified these as dot products in this way, V1 dot A1 and V2 dot A2, that these naturally are in the opposite directions. Now note what's interesting is that this value is actually negative at the inlet to the control volume, whereas this is positive at the outlet, and that is a definition that will be important. So the net mass outflow is just going to be rho times the velocity times A. If you remember, this is the mass flow rate, and so if we just multiply these by the densities, then we have this equation, and we can start to specify how much mass is going in and how much mass is going out. But remember, the mass going out is positive, whereas the mass going in is negative. It's kind of a strange definition, which is basically because of these vectors. So let's relate this back now to intensive and extensive properties and start to derive the Reynolds transport theorem. So we can see that down here, this is going to be important for that. So to obtain the net rate of flow of any extensive property, we need to take our little b times the mass flow rate, m dot, and that will give us the amount, since the masses cancel out here, if I go ahead and cancel those, we see now that this is really just B, capital B dot. It's the amount of our quantity of interest per time. So now we're getting to something where this is now something that might be of interest to us. How is the momentum changing inside a control volume? How might the energy be changing in time in our control volume? So we can see that we're starting to have the building blocks for understanding as mass flows through a control volume, how we get at the time rate of change of our quantity of interest. So we can sum all the inlets and outlets, and we can basically have the net change of our property in time just be B times the mass flow rate, m dot. And in general, we can replace this summation with a integral over our control surface. This might be a cross-sectional area or something like that. So in general, we write it like this. So let's continue on. We're now going to begin to relate this to the Reynolds transport theorem. And let's just state in general what it is. It's an equation that relates a derivative or change for a closed system, that is for maybe the closed system of a parameter of interest, the capital B, it might be energy or momentum or mass, to the corresponding terms from a control volume. So what that means is we're going to basically be equating the Lagrangian and the Eulerian points of view. Remember, they're equivalent. They're just different expressions of the same phenomenon in a different way of looking at it. It basically relates Lagrangian point of view to the Eulerian reference or Eulerian approach. So how does this work? Here we have a control volume in here, a fixed control volume, and we're not allowing this to change in time. We're just saying we're interested in what goes in and out of this box. And we realize the flow is coming in here, and we've got this little parcel of fluid that's going to be injected into the box. When we allow that to happen at a time t, delta t later, so this is at time t, at a time delta t later, we've actually realized some outflow here. The inflow has gone and pushed some of the fluid out. So we're interested in now developing what equations that describe how the quantity B changed from time t to time t plus delta t. So what is the state of the closed system at time t? It's this. The state of the closed system is just going to be the amount of stuff in the control volume plus this little delta B that's going to go in. Okay? What is the state of the closed system at time t plus delta t? It's just the same thing, except now we have the state in the control volume, we're at state t plus delta t, and we have this B out on the other side that's come out of the other side. So basically, let me go back to this. What we have is the dark area here is our control volume, or I'm sorry, is our fixed quantity of fluid, and we're watching it as it gets basically pushed out through this other little nozzle, that other little outlet. So let's combine these equations. So if we look at the rate of change of the extensive property, the full derivative of the change of the closed system, the dark fluid there, in time, that's going to be basically the limit as time goes to 0 of bt plus delta t minus b of t, all divided by t. And what we can do now is we can re-express this as being, and this is the derivation is in the book. I'm not going to go through all of this. What we really need to do is we really need to get to this equation. So if you want the details of how this is done, you need to read the book carefully. But basically, we have the total derivative of the closed system can be rewritten as dt of the control volume, the change in anything, the change in the control volume of what's in the control volume, plus the net rate of change of that quantity in the control volume. And so what we have, b dot net is just basically the rate of flow out and the rate of flow in. And remember, the positive sign is on the outflow. Positive is outflow minus whatever comes in. Now, we can rewrite that equation in terms of the rho dV that we've been using all along. And so what we have is a Lagrangian point of view, dB dt, the total derivative of B with respect to t in the closed system, is going to equal these two terms, the Eulerian terms, where we have the rate of change of matter in the control volume. Many times this will actually be 0 because stuff will be going in and out of the control volume at the same rate. Let me state that differently. Basically, the rate of change of the volume will not be changing, and these terms are just going to relate what's going in and what's going out minus what's going in through the control surface. So this is the Reynolds transport theorem. In words, what is this? It says this term here is the rate of change of property B in a closed system. A lot of times we're interested in this, in calculating what this is. But a lot of times it's hard to do that, so we use the control volume approach. The first term here, this term, is the rate of change of the property in the control volume. And that's going to be added to the net outflow. Remember, outflow is positive. So this is the net outflow of property B through the control surface. So in order to calculate this, a lot of times we're going to be looking at calculating the outflow out one end and minus the inflow in the inlet. This can be expressed in other forms. I'll just go through these quickly. You can see that the equations are a little bit different here. We've replaced this integral with a sum, and This is going to be the case if the intensive properties are uniform across each pore. So things are going to be simplified if we know we have uniform flow. We can simplify this even more. If there are a number of inlets and outlets, the intensive property B and the intensive property is uniform across each of the ports, then what we and that's not even the velocity and density don't even need to be uniform. Only the property that we're interested in. So if we have that, then we can just write the sum of the outlets minus the sum of the inlets. So we can have quite a complicated system with many outlets and many inlets. And as long as we knew that the flow of our property B was uniform across those inlets and outlets, we'd be able to simplify this equation. So that is the Reynolds transport theorem. We're going to be using this quite extensively, either in this form, or perhaps even this most general form. Quite honestly, a lot of the problems that we deal with, some of the problems that we deal with will use this equation, and a lot of times the control volume, this term actually goes to 0, and all we need to do is account for the outflows minus the inflows. So this will be possible, but in its general form, this is the form of the Reynolds transport theorem we'll be using quite a bit. So what we need to do now is move forward from the abstract. This is quite an abstract concept right now, and we need to move past this and start to apply it. And the first thing we're going to apply it to is mass through the continuity equation. And I think once we start applying this, we will see that it can be used for conservation of mass within a control volume. We will see the utility of the Reynolds transport theorem. So hang in there. Let's just note that we have an idea of what this Reynolds transport theorem is, and now we're going to start to apply it to mass. And in the next 2 chapters, we'll apply it to momentum and energy. Thank you.